This is the 17th video in a series related to abstract linear algebra, and this is perhaps the least abstract video that we'll look in this whole series. But that being said, it is something that we need to go over, but we're not going to go over it in a ton of depth because this is something that is generally taught at a much lower level, like a standard high school algebra course. Maybe not quite as in-depth, or maybe a standard basic elementary linear algebra class. Okay, so anyway, let's get into it. Our goal today is to look at solution techniques for the system of equations represented by the following matrix vector equation, ax equals y, where a is an m by n matrix, x is like an n vector, and y is an m vector. Or equivalently, the following system of m equations with n variables. So we've got a11 x1 plus a12 x2 all the way up to a1n xn is equal to y1. So that's our first equation. We've got a similar second equation all the way down to this mth equation, which is am1 x1 all the way up to amn xn equals ym. And I'd like to point out that this whole system can be represented by something called an augmented matrix, which is really just a tool for bookkeeping. And that's given with the coefficients on the left-hand side. And then often there's this like vertical line, and then the maybe solution part on the right-hand side. So notice we've got our aij here, and then our yi over here. Now, I'd like to point out that we have the following sort of canonical operations that we could do to a system of equations, which are directly related to doing some operations on the associated augmented matrix. And the important thing about these operations is they do not change the solution set to the system of equations. So our goal is to find the solution set for a system of equations. And really kind of the strategy for working towards this goal is to simplify that system of equations until we can really just read off the solutions. Okay, so there are three main things that you can do to a system of equations that will not change the solution set. And like I said, those can be mapped over to three operations on the augmented matrix. So the first thing that you can do is interchange any two equations. So what I mean by that is you just take one equation and another one and you swap them. Well, clearly that is not going to change the solution set at all. That's keeping the same data like coded in here. We're just like changing the order a little bit. But over in the augmented matrix, that's the same thing as interchanging two rows. So I've got notation here. This is like the ith equation and the jth equation being interchanged, whereas this is the ith row and the jth row being interchanged. The next thing you can do is scale an equation by a non-zero constant. So in other words, you could take like equation I and multiply it by alpha, where alpha is not equal to 0, and that'll become your new equation I. So that's clearly something that you can do as well. In fact, if you're solving a system of one equation and one unknown, you often do that at the very end. You divide by the coefficient of whatever the variable is. And so this is just that kind of in general. And that's equivalent in the augmented matrix world as scaling a row by a non-zero constant. So in other words, we would take the ith row and replace it with alpha times the ith row, where alpha, like I said, is a non-zero constant. Then the last thing that you can do is add a multiple of an equation to another equation and then make that replacement. So in other words, you could take equation I, you could add alpha times equation j, and then replace our original equation I with that new equation. And so that's equivalent in the row world to replacing row I with the old row I plus alpha times the row j. So this is a little bit trickier to talk about, but it doesn't change the solution set. And also, I have a little trick just to keep things organized. I often put the row that I'm changing on the outside here. So that would be like row I or equation I. And then I put the row that I'm using as a tool in the middle here. So that would be like equation J here or row J here. So you can think about your goal to simplify row I or equation I, and you're using row J or equation J as a tool. Okay, so before we look at some examples of this in action, let's get the idea for kind of a solution, maybe strategy here. So here's a path to a best case scenario for solving a system of equations. So for this path, I'm just going to look at a square matrix, or in other words, we have the same number of equations as unknowns, although in our examples, we'll see cases where that is not happening. So let's start down here. Let's say we've got a system of n equations and n unknowns. So our unknowns are x1, x2 up to xn, and these are our n equations. So the first thing that you would do is take that system of equations and write it as an augmented matrix. So here we've got a square n by n matrix, but like I said, that won't always be the case. And then we put our solutions over here, this y1 down to yn. Then the next step, which is really the big calculational step, is to do simplifying row operations towards the goal of turning this matrix into the n by n identity matrix. In other words, we should just have ones on the diagonal. Then you turn that back into a system of equations. But now the system of equations is quite simple. You just have x1 is equal to b1, xn is equal to bn, where the b's and the y's are related by, well, the y's turn into the b's by whatever row operations you apply right here. Like I said, this is the best case scenario, but in our examples, we'll look at cases where this doesn't happen. Okay, let's maybe jump into some examples. So let's start off with a fairly simple system of two equations and two unknowns. So we have x1 plus 2x2 is 5, and then we have 3x1 minus x2 is 1. So we would start by turning this into an augmented matrix. So we would have 1, 2, 5 in the first row, 3 minus 1, 1 in the second row. And now we're going to do row operations to turn this matrix into the identity matrix. Well, hopefully. As we'll see in a bit, the goal really isn't the identity matrix. It's something called a reduced row echelon form of this matrix. Okay, so what's the first step we'd like to do? Well, we've already got a 1 kind of in this upper left portion. Maybe we want to put some zeros underneath because that would be the shape of the identity matrix. Now, what row operations could we do for that? Well, we could take row 2 and subtract 3 times row 1 and turn that into our new row 2. That's because 3 minus 3 times 1 is 0. So let's see what that leaves us with. The first row is not changing, so I'll copy all of the rows that aren't changing down. There's only 1 in this case. And then I have 3 minus 3, that's 0. Then I have negative 1 minus 6, that is negative 7. And then I have 1 minus 15, that is negative 14. Negative 14. Okay, good. And now the next thing to do would be to scale row 2. So let's do that. So we'll take row 2 and multiply it by negative 1 over 7, and that'll be our new row 2. So that's going to give us 1, 2, 5 in the first row, 0, 1, 2 in the second row. Now we can finish this thing off by subtracting 2 times row 2 from row 1, and that'll finish the shape of the matrix that we're going for. So let's write that down here. So we'll take row 1 and subtract 2 times row 2, and that's going to be our new row 1. So let's see what that leaves us with. We'll have 1, and then 2 minus 2 is 0. We have 5 minus 4 is 1, and then row 2 didn't change, so we have 0, 1, 2. And then from here, we rewrite this augmented matrix as a simple system of equations. We have x1 is equal to 1 and x2 is equal to 2. And that would be the solution to this system. Okay, now that we've got the basic strategy down, let's introduce the concept of a matrix in reduced row echelon form. Now we're going to look at the notion of the reduced row echelon form of a matrix, and we'll do that via this definition. So we say a matrix is in reduced row echelon form. We sometimes shorten that as RREF if the following 4 rules are satisfied or characteristics are satisfied by this matrix. So the first is that all 0 rows of this matrix are at the bottom. The second is that the first non-zero entry of every row is equal to 1. And that's called the leading one of a row. And then next, the leading one of a row is strictly to the right of leading entries in higher rows. And then finally, the leading one of a row is the only non-zero entry of a column. So we'll look at examples of matrices in RREF or reduced row echelon form to get an intuition for what they look like. But before we do that, you might ask, well, why would we have this sort of definition? And that's based off this kind of like nice property that if you take an augmented matrix based off a system of equations, so I've written the augmented matrix like this, then you do row operations until the matrix is in reduced row echelon form, then it's actually fairly easy to look at the solution set or to see the solution set of this system of equations. And since these row operations didn't change the solution set, that means we've got the solution set for the original system of equations. Okay, well now let's look at some examples of matrices in reduced row echelon form, as well as the solution sets to the associated system of equations. So here are 3 examples of matrices in reduced row echelon form. And I guess I should say here that when we're talking about the reduced row echelon form of a matrix, with respect to the augmented matrix and solving systems of equations, we're really just talking about getting the coefficient matrix, the thing to the left of the vertical line, into reduced row echelon form. Okay, so I've got some examples up here of matrices in reduced row echelon form, and we're going to look at the solution set for each one. I've worked one out already because it's the simplest. So if we get the matrix in reduced row echelon form and it's the identity matrix, then really we can just read off the solutions from this column over here. So x1 is 3, x2 is -5, and x3 is 4 in this case. Now let's see what we have in this second example. So here we've got our augmented matrix, which is in reduced row echelon form. Notice the first non-zero entry of every row is a 1. The 0 row is at the bottom. Notice really all I want to look at is the 0 row of the coefficient matrix. And then every row with a leading 1 has zeros everywhere else in the column. So we do satisfy these rules over here. That's good. So now let's rewrite this as a system of equations. We have x1 minus x3 equals 4. We have x2 plus 3x3 equals 2. And then notice down here, this doesn't provide any more information. So that means that one of our variables is kind of free to be anything. And the standard choice to make is that the variable that's based off of the column without a leading 1, these are sometimes called pivot columns, is the free variable. So notice we've got a leading 1 in this column, not the third column. So that means we say x3 is a free variable. It's free to be anything. But that gives us a parameterized solution set by this free variable. The standard way to write this would be x1 is equal to 4 plus x3, and then x2 is equal to 2 minus 3x3. And then like I said, x3 is our free variable, so we'll just put free here. So that'd be our solution set. Since x3 can be anything we want, that means, in fact, there are infinitely many solutions here. Now let's look at this last example. So we have the same matrix, which is in reduced row echelon form. Here, I really want to underscore the fact that we're just looking at the coefficient matrix, because if we look at the entire matrix, it is not in reduced row echelon form. given that we've got this like 3 here, which is the first entry of the third row, if again we like don't cut it off at the coefficient matrix. Now let's turn that into a system of equations. Notice we have the first 2 identical to the one above, so that would be x1 minus x3 is 4, x2 plus 3x3 is 2. But then let's read off the meaning of this third row. Well, it would be like 0x1 plus 0x2 plus 0x3 equals negative 3. In other words, it would be 0 equals negative 3. But 0 equals negative 3 clearly does not make any sense. That gives us some sort of contradiction. So that means that this is a empty solution set. So in other words, there's no solution to this system of equations that would reduce to this following augmented matrix in reduced row echelon form. Okay, so let's clean this up and then work through an example. Okay, let's say we've got the following system of 3 equations and 4 unknowns, and let's use our strategy that we've outlined to find a solution set. So the first thing that we'll do is take this guy and turn it into an augmented matrix. So notice the augmented matrix will be 2, negative 2, 1, 0, 4. Since we've got 4 variables, we want to make sure to encode the fact that the coefficient of x4 here is 0. Likewise, the coefficient of x1 and x2 in the second equation is 0, so that gives us 0, 0, 1, 2, and then 1. And then finally here we have 2, minus 2, 2, 2, 5. Okay, nice. And now we'd like to manipulate this until we get it in reduced row echelon form. So how can we do that? Well, maybe the first thing that we can do is zero out this 2 here, given that we'd like to have only a single 1 in that row, or in that column. Okay, now how can we do that? Well, we could maybe take row 3 and subtract row 1 and let that become our new row 3. So let's see, that's gonna give us 2, negative 2, 1, 0, and then 4. And then row 2 is not changing, 0, 0, 1, 2, 1. Then row 3 is changing. We have 2 minus 2 is 0. Negative 2 minus negative 2 is 0. 2 minus 1 is 1. 2 minus 0 is 2. 5 minus 4 is 1. So we're left with something like that. Okay. And now from here, let's notice that the second and third rows are the same. So that gives us motivation to taking row 3 minus row 2 and making that our new row 3, because that'll just cancel out. So that means row 1 and row 2 are not changing again. We have 2, minus 2, 1, 0, 4. And then we have 0, 0, 1, 2, 1. And then we've got a row of all zeros. Notice that row of all zeros is already at the bottom, so that means it's obeying this first rule already. Okay. Now, let's note that we can have a 1 as the first entry of this second row. We can use that to zero out that third column. So maybe we would want to do that by doing row 1 minus row 2 becomes our new row 1. That's going to zero out this entry. Okay, so let's see. That's going to give us something like 2 minus 2, 0, 0. And then let's see, 4 minus 1 is 3. And then here we'll have 0, 0, 1, 2, 1, and then 0, 0, 0, 0, 0. Great. And now this is almost in reduced row echelon form. All we have to do is multiply this first row by 1/2. So let's do that to finish this whole thing off. So 1/2 row 1 becomes our new row 1. And then we have something like this. 1, negative 1, 0, 0, 3. And then 0, 0, 1, 2, 1, and then all zeros. So let's maybe bring that up here and we'll write down the final solution. So this is where we left off. I fixed a slight typo that was on the last board, but we got our augmented matrix into reduced row echelon form, so that's good. Now we can transform this back into a system of equations. Notice we have x1 minus x2 is equal to 3/2. And then we have x3 plus 2x4 is equal to 1. But then notice that there are no leading ones in the second or fourth column. So that means that x2 and x4 are both what we'll call free variables. So that allows us to write a parameterized solution here. x1 is equal to 3 over 2 plus x2. x3 is equal to 1 minus 2x4. And then x2 and x4 are free, like I said. Okay, so now I'll give you guys a couple of warm-up problems based on this stuff. So here are 3 kind of associated warm-up problems. So these are systems of equations. So this first one and this last one is a system of 3 equations and 4 unknowns. So we've got x1 minus 2x2 plus 3x3 minus x4 equals 0, minus x1 plus 2x3 plus x4 equals 0, and 2x1 plus x2 minus 2x4 equals 0. So the fact that we all have zeros over here means that this is something called a homogeneous differential, or a homogeneous system of linear equations. And then this next one is x1 plus x2 minus x3 is 1, 2x1 plus x2 plus 3x3 is 2, and x2 minus 5x3 is 1. And then this last one is another system of 3 equations and 4 unknowns. I'll let you read that off. And that's a good place to stop.